So the central limit theorem tells us that the normal distribution is going to show up a lot of the time. And in part because of this, the normal distribution is often used for inference in canonical statistics. So let's take an example from the wiki where you know that there are students in a geographical region, and the mean and standard deviation of scores on our test are 100 points and 12 points. So the students are getting an average of 100 plus or minus 12, where 12 is the standard deviation. And importantly, we know this ahead of time. Okay, so you guys know that when we get to the t-test, we're going to have to make corrections for estimating the variance from a population. But now we know this ahead of time for this first simple example. This is pretty easy to model up in R. We can say from students getting a 0 to a test to a 200 on a test, we can just use dnorm. We know the mean and standard deviation ahead of time. And so we can plot this probability density function. Again, as we talked about in the previous lecture, this doesn't actually capture all of the probabilities because the dnorm is actually defined from minus infinity to positive infinity, but below 0 is vanishingly small, and above 200 is also vanishingly small. It's not actually possible to get a score below 0, so the math sort of disagrees with the interpretation of the data, but it's fine because it's so close to 0 that we can basically consider this to be 0. So we can go ahead and model this through permutations. So we can say, okay, just take a million permutations, and we have we'll sample between 25 and 175 again, because below 25 or above 175, what's going to happen? The number of students that are getting scores below 25 or 175 are vanishingly small, so we'll only have to model in this region here. And again, to be completely mathematically correct, you'd have to sample between minus infinity or positive infinity. But that's not possible. So at some point with the normal distribution, you do have to make a cutoff and say it's going to happen so infrequently that a student scores 25 that I'm not even going to sample down there. The analytical norms are just from dnorm, right? The analytical norms are just given by the probability density function for the normal distribution, or I can sample R norm with those permutations, right? So I can say simulate a million students taking the test with a mean of 100 and a standard deviation of 12, right? So this dnorm is going to be, of course, the probability density function. The R norm is simply going to be sampling from this normal distribution a million times with a mean of 100, standard deviation of 12. Of course, these are the same thing when you put them in histogram, right? So I make the histogram and I get this perfect normal distribution because I'm sampling from the normal distribution. And then I just have to scale my dnorm so that it's on the same scale as my sampling. And of course, this matches up perfectly. And by the law of large numbers, the mean is almost exactly 100 and the standard deviation is almost exactly 12. Okay, so that's fine, but this is not in standard normal form. So we know that actually for inference, we need to convert this into standard normal form. And the trick to that is going to be subtracting off the mean and dividing the standard deviation. So we're going to go through two important proofs here. These proofs are going to be very useful for us in understanding why the t-test works the way it does. The first proof is that if you add a constant to each data point in a distribution, okay, so we have a mean, which is just our canonical definition of mean, right? The sum of all the data points divided by n, and a variance, which is our canonical definition of variance, which is xi minus the mean squared divided by n, right? And we're not going to worry about the n minus 1 here because we know the standard deviation ahead of time, so we don't have to make this correction for n minus 1, at least not yet. So given these definitions of mean and variance, if we add a constant m to each data point, so I go back and if I want to add to all of my million exam scores, I want to add or subtract a constant, what happens? So we can prove very easily that the mean will shift by mean plus m, right? Because I'm adding a constant to each data point, right? And so that equals this sum plus this sum, but the sum of m divided by the sum of m n times divided by n is just m. Right, so this just resolves to m, and that's the definition of the mean. So if you add a constant m to each data point, the entire distribution is going to shift by m by the constant that you've added. What about the variance? Well, it's actually pretty easy to show that the variance doesn't change. So here I have xi plus m minus mu, right? So the variance is just xi minus mu. Now I'm adding m to this term here, and I'm adding m to this term here. So this is just xi plus m. This is the mean, right? Sum of xi divided by n is the definition of the mean. M n times is m times n divided by n, which is just m. Now the m's cancel out. So it turns out the variance doesn't change. So if you add a constant to each data point, you shift the location of the curve without changing the variance, and it's very easy to prove that analytically. So let's go ahead and do that in R for our example exams. So I have my my analytical norms here with a mean of 0, standard deviation of 12. I have my permutations. I subtract off my mean permutations here. So I get permutations equals permutations minus mean permutations. I make a histogram of all of these, right, as before. Everything is exactly the same. The standard deviation is still 12. The standard deviation hasn't changed at all. But now I'm centered over 0. And if I take the mean of these permutations, that's indistinguishable from round off, centered over 0. Okay, so that's fine. Now what happens if we multiply each data point by a constant? Okay, so if we multiply each data point by a constant, so I start with my definition of a mean, and I multiply that by the constant m. And so if I do that, I get the sum of m times mx. So this m here is a constant. It just comes out here. But the sum of m times means that's just m, right? So this is just a constant. So I can take it out of these parentheses, right? And so that's just m, right, times the mean. And that's just mu, right? So this constant just can pop out of this parentheses. It can pop out across the sums, and that's just equal to mu. What about the variance? So now I have mix minus mu. So now if you factor this out, right? So we have ma minus mb squared equals m squared a squared minus 2 m squared ab plus m squared b squared equals m squared a squared minus 2ab plus b squared equals m squared a minus b squared. So this proof here tells us that when we have this m here, the m is going to come out as an m squared, just substituting in here, right? So the m comes out as an m squared. So the variance equals m squared times the original variance. So if you multiply each data point by a constant, the new mean is m times mu, the old mean, and the variance changes by m squared, not by m, but by m squared. And again, this is going to be very important when we actually calculate the standard error of the mean and start to work towards the t-test over the next lecture or two. So here, if I have my distribution and I want to make it in standard normal distribution, the first thing that I do is I subtract off the mean, right? So I subtract off the mean, and now the new mean equals 0, right? Once I've subtracted off the mean, and now I divide by the standard deviation, right? So if the new mean equals 0, and I divide by the standard deviation, multiplying mu times 1 over the standard deviation is going to be 0 when mu is 0. So mu stays 0, so the mean stays 0, which is what we want. And when I divide by the standard deviation, the variance, right, the variance is going to become 1. So if m squared, m squared sigma squared is what happens. If m squared equals 1 over the variance, right, this is going to reduce to 1, right? So I'm dividing by the standard deviation. The standard deviation squared is the variance. So m squared is going to equal 1 over the variance, and 1 over the variance times the variance equals 1. So the standard deviation and the variance are both going to be 1. So all that I have to do in general to take any distribution is divide by the mean or subtract the mean and divide by the standard deviation. And this, of course, gives us the standard normal distribution. So this is what you get in R by default when you type d norm or p norm. So here's the probability density function, and here's the cumulative distribution function. And so this is maybe something that you memorized in your first semester stats class, which is that the area under the curve, right? So if you're 2 standard deviations away, the area under that curve is 0.02, right? So in a 2-sided test, if you're 2 standard deviations away from the mean, that's around a 0.05 p-value, right? So that's a fact that we kind of memorize about the normal distribution in a first semester stats class. So from here, minus 2 out to negative infinity is around 2%, 2.2% of the probability density function. Since of course this is perfectly symmetrical, going from 2 out to positive infinity is another 0.02%. So for a 2-sided test, if you're 2 standard deviation units away from the mean, that's about equivalent to a 0.05, which is of course the magic threshold in frequentist statistics. So we just showed that if you have any data set that's normally distributed, you can trivially change that into the standard normal distribution by subtracting off the mean and dividing by the standard deviation, and you'll get the standard normal distribution. And just using this fact, we can do some simple inference on our exam situation. So let's say that we have, in this example, right, so remember our example is that the students have 100, the average is 100 points and the standard deviation is 12, right? And so what happens if you have a single student, one student, who scores a 125, right? So the null hypothesis is that student was drawn from the same geographic region. Right? And so even, again, just by memorizing, right, 125 is around 2 standard deviation units away, right? So we know that this is going to be just a little bit smaller than 0.05. We don't even have to type anything into R if we have this fact memorized, right? But we can express this in terms of the standard normal distribution, right? We're taking our data point and we're changing it into a data point that comes from the standard normal distribution by subtracting off the mean of the distribution that we're testing against and dividing by the standard deviation. Right? And so when we do that, we get 2.083, right? And so we can sort of read this as this 2.083. So for a one-sided test, and if this was a two-sided test, right, because the null hypothesis is that the student was drawn from the same geographic region. We didn't say that the student was doing better or worse than average, just drawn. So we get our z-score, which is our z-score is defined as how many standard deviation units are you away. The z-score is around -2, so we know that the p-value is going to be around 0.05. And so we type all this into R and we get a p-value of around 0.04. It's a little bit more than 2 standard deviations away, so the p-value is a little bit less than 0.05. So let's just make a sanity check as we like to do. And let's just make sure that if we do this over and over again, that we can generate a uniform distribution. So here I have 100,000 trials. I'm going to sample one student taking one exam from a mean of 100 and standard deviation of 12. Then I'm going to calculate the z-score, right? The z-score is how many standard deviation units are you away, right? Subtract off the mean, divide by the standard deviation. How many standard deviations are you away? Make this a two-sided test, right? And so our p-value is just going to be p norm a value, right? What's the cumulative distribution function? How far are you away from that mean? And so if I do this over and over again, with the null hypothesis being true for my single student, I get a uniform distribution of p-values. Right? The null hypothesis is true, so this is a correct statistic for sampling one student from the normal distribution and then testing against that same normal distribution. The same thing that we've been doing over and over again this semester, but this time with the normal distribution. But now something interesting happens if we increase the number of students we see to that got a score of 100 to 10. Right. So now I am taking a look at 10 students. Right. So remember that when I type R norm 10 here, like we can see this easily enough in R. Right. So if I type R norm 1 with a mean of 100 and standard deviation equals 12, I'm sampling one student. Oh, the student got 106. They got a 90. They got 103. Right. If I do 10, now I'm having 10 students take the test, right, with the same mean and the same standard deviation. So now I'm having 10 students take the test, and now I'm going to calculate my z-score from the not from one student, but from the mean of these 10 students. Now this mean is still going to be 100, right? It's still going to be centered on 100. The average of these 10 students with the expected value is still 100, right? But when I do this simple statistical test, I see that I'm breaking my my p-values. In fact, the p-values are larger than you would expect. So this is not the correct inference for when you have more than one student taking the test and you're taking the average. And so we have to actually put into our test statistic some information about how large the sample sizes are. So we want to know how do we calculate how many standard deviation units are we away from the mean when we have more than one student taking the test. So we want to get the standard deviation. How do we calculate that standard deviation? How do we put the sample size information in when we have more than one student taking the test? So this proof gets a little bit involved, but it's not that difficult to follow. So consider 10 students taking the test, right? And let's define the sum of y as the sum of these 10 scores, right? And so the value, it's pretty easy to see that the expected value of the 10 scores is 1,000, right? So I have 10 students taking the test. I expect each student to get 100. So my expectation of the sum of all their scores is 1,000, right? And the expected variance of this sum is n times the variance. So it's going to be 10 times the variance. So actually the expected variance is going to be 10 times 12 times 12, right? So to see that, right, consider that for the variance is defined for just one draw is the sum of their score minus the mean squared, right? That's the variance for one draw, but these are just sums. So if I have 10 students taking the test, I just sum these 10 together, right? So I have that sum 10 times. So the variance of the variance of the sum is just going to be n times SD. I'm just going to sum these together. Right? So that actually proves this analytically, and we can see this easily enough in R. So here I just have 10,000 students or 100,000 students take the test with a mean of 100 equals standard deviation of 12. Right, I'm going to sum 10 students taking the test, right? So this is the sum of the 10 students taking the test. This is the sum of the y. My expectation of the mean of that is 1,000, and sure enough, that comes out right at 1,000. And my expectation of the variance is this n times 12 times 12, n times the standard deviation squared, or n times the variance, which is 1,440. And sure enough, that's where the variance comes out of these sums. Okay, so that's fine. So how does this help me get to what I'm trying to get to, which is calculating the standard deviation, the appropriate standard deviation to use? So what I want, right, is what I'm looking at here in my test is the mean, not the sum. So I have to convert the sum to a mean. Okay, all right. Well, that's easy enough to do, right? To convert the sum to a mean, I just divide by n, right? So the expected mean of the sum was n times mu. But I'm dividing now by the mean. So this is just n times mu divided by the by n. So that's just mu, right? So we're relying on this rule that we proved here, that when you multiply a constant, when you multiply distribution by a constant, the new mean is m times the old mean, right? So I'm multiplying the sum here, where my mean is n times mu. I'm multiplying that I'm dividing that by n. I'm multiplying it by 1 over n. So the new mean is n times mu over n, right? So that's just the mean. So that's just 100, right? And the variance of the mean, right, becomes st squared over n, right? Because this was n times st squared, but I'm dividing by n, right? And when you divide this by n, it changes by n squared. Right, so this is the rule that we had here, right? That when you make this division, the variance is going to change by n squared. So for the sum, I was expecting the variance to be n times st squared. To get to the mean, I divide by n, right? And so dividing by n will change this by 1 over n squared. So the expected variance becomes st squared over n. Right? And so in order to, and so let's go ahead and so that proves that analytically. So the expected value of the mean is just the mean. That's not surprising. But the expected variance of the mean we're trying to get is the original variance of 12 divided by the sample size divided by 10. And so this proves this analytically. And again, this is dependent on this idea that when you multiply a distribution by a constant, the variance changes by that constant squared. Right. So that's all. Lots of analytical stuff to follow, but not so hard to put into R. Right. So here I have the mean of the right. So before I had the sum, but now I'm interested in the mean. And so I have the mean of my 10 distributions of mean equals 100, standard deviation equals 12. Of course, the mean is just 100. I actually don't need any math to know that. The mean is going to be 100. But the variance, this is the thing that I did learn that I didn't know before. The variance of this mean is now going to be 14.4, which is the variance, right? 12 times 12, 144 divided by the sample size 10. Right. So that this proof here worked out when we actually looked at the numbers. Now if I take the square root of this, right, the square root of this is how many standard deviation units am I going to be from the mean. So I can use that for inference. That's the correction that I'm looking for inference with the sample size, and that gives us this familiar formula for the standard error of the mean. So if what I just said makes absolutely no sense to you, there's a really nice description of all this on the wiki that you can go and look at, and that's actually a reasonable description. So what does this mean in practice, right? So for our inference in practice, right? So consider just the student taking one exam, right? So if the student's just taking one exam, right, the mean is still 100. The mean's always going to be 100, right? The sample size is not involved in the formula for the mean, right? The sample size is not here. It's only involved in the standard deviation or the variance of the mean. So the mean's always going to be 100, no matter how many students are taking the exam. So here I have one student taking the exam, right? And I do that 10,000 times. The mean is 100. The standard deviation is 12. So this is just the simple test that we saw before for a single student taking the test. And the distribution is going to look like this, right? So with a mean of 100 and standard deviation of 12. But now if I take the average of 4 students taking the test, right? So now instead of having one student take the test, I'm having 4 students take the test, and I'm taking the mean of that. The mean of that is still 100, right? The mean's not going to change, but now the variance is starting to come in because the standard deviation is now going to be equal to 12 over the square root of 4, which of course is 6, right? So so the standard deviation, when I'm taking the average of 4 students taking the exam, the standard deviation moves from 12 to 6, right? And so when I do inference, if I go 2 standard deviation units away, right, I have much more significance than if I go 2 standard deviation units away when just one student is taking the test, right? And again, intuitively, you can think about this. If 1 million students take the test, the mean is going to be very, very close to 100, right? If only one student takes the test, it's much more likely that you could get a student taking 60 or 120, getting a score of 60 or 100 or 60 or 120. If one student takes a test, it's possible that student is going to get a 60. And 1 million students take the test and you take an average, there's no way that average is going to be 1 million, right? So the standard deviation has to come in. And the proof that we just did shows us how the standard deviation comes in. It comes in as the way to correct for the sample size is to divide by the square root of the number of students taking the test. And we can keep doing this, right? If 10 students are taking the test, then the standard deviation becomes 12 divided by the square root of 10. If we're taking the average of 10 students taking the test, if 100 students take the test, the mean is going to be very close to 100. So for inference, the way this is the test that the correction that we need to make is to put the number of students taking the test, put that correction into the estimate of standard deviation of how many standard deviation units we are away from the mean. So to look at this example from the wiki, so this wiki says you have your background distribution of 100 students taking the test with a standard deviation of 12. What if 55 students take the test? Right, so 55 students take the test and they receive a score of 96. Right. So is it possible that these students were drawn from the same district with a null hypothesis that the students were drawn from the same district? So our standard error in this case is 12 divided by the square root of 55, right? And so this is our new standard error of 12 divided by the square root of 55. Our z-score now for the z-test, we were 4 units away, and we divide by this corrected standard error. So that turns out to be 2.47 units away, and for a one-sided test, the p-value of that is 0.006, or if you double that one-sided test, you'll get a two-sided test of 0.014. So this idea of the standard error of the mean is just that we have to correct for the in order to figure out how many standard deviation units we are away from the mean, we have to know the sample size. Because if you have a large number of students taking the test, you expect to be much more close to 100 than if you have a small number of students taking the test. So this should all be review from last semester. But again, you can sort of think about it intuitively in terms of the extremes. If n equals 1, sampling from a null population, so as n is greater than 1, as you sample from a null population, you get closer and closer to the mean because of the repeated sampling. And of course, at n equals infinity, you're going to be at exactly the mean by the law of large numbers. Right? If you're taking the average of an infinite number of students, that average will be exactly 100 by the law of large numbers, and any deviation from that will be statistically significant. This can actually sort of be a problem for bioinformatics, where when you end up with very large sample sizes and you can get very small p-values for very small differences, and you have to ask yourself, are those differences really biologically relevant? So to return to our code, so here was we left our code in a broken state, in a bad state, where our test wasn't working because we were underestimating or overestimating the variance. So here we have 10 students taking the test, and I know now that I need to, when I want to ask how many standard deviation units am I away from the mean, I have to actually correct this 12 by dividing by the square root of the sample size. right? So all I have to do to make this uniform again is add the square root of 10 here, right? So now I have the standard error of the mean instead of just the known ahead of time standard deviation. And I do this, and my uniform p-values are restored. And so now if I'm sampling 10 students and taking the average of those 10 students, the math that we just did, the analytics that we just did, says that if I correct the standard deviation for the sample size by dividing by the square root of the sample size, and then do statistical testing against the same distribution that I drew from, I'm going to get uniform p-values, meaning that this test is correct. Just as a second sanity check, if I move the test over a little bit, right? So I move the average test score from 100 to 102, I get small p-values. So we've seen this over and over again over the course of the semester, right? So if I take this, if I sample from a mean of 102, but test from a mean of 100, even though this is a very small difference, my p-values will be much smaller than you would expect under the uniform distribution, because as we've seen all semester, when you have an adequate sample size, if you sample from and here I have 55 students taking the test, especially with sample size of 55, it doesn't take a very big difference to generate small p-values. And again, the question would be: is this a meaningful difference? Is it a statistically significant difference? But is it a meaningful difference? Does it matter that the students got 2 points higher than you were expecting by background? Is that real improvement or is it not? And so that becomes a policy question, or a question for sociology, or interpreting whatever this change is in terms of the politics of your local school system or whatever. But that's really a separate question from whether it's statistically significant question. It's a statistically significant difference.